Okay, so welcome back, everybody. Um, yesterday we finished our discussion of, well, mostly um, we had done this generalization. We had talked about the heat equation in 2D and using separation of variables on it. And so now I want to do kind of a similar discussion for the wave equation and see what that leads to. And as we'll see, this this formulation is going to lead to something called Bessel functions. So these are going to arise as our like analogous eigenfunctions to sine and cosine as before. Um, and so we'll see how this works. So the example I want to consider is 2D wave equation. So 2D wave equation with Dirichlet boundary conditions. So what does that look like? So our wave equation in 2D is u sub tt is c squared times the Laplacian of u, which of course we could write as, if we like, c squared times u sub xx plus u sub yy in the 2D case. Okay, and that is for x in D. Now, let's do this. So, let's do this in, say, the unit disk, right? So let D be the unit disk. So we'll say the open unit disk. So the set of ordered pairs xy is such that x squared plus y squared is strictly less than 1. Okay, so what does D look like? It is our usual unit disk. All right, so here's one. Okay, well, if that's the case, then of course the boundary of D is unit circle. So let me draw that in. Right here it is. There's the boundary of D. Okay, so Dirichlet boundary conditions on this boundary would amount to, if they're homogeneous, right, this would be u is equal to 0 on the boundary. We'll write, just so that we can conveniently do this, let's write this as a vector. This is for x in the boundary. And then we have initial displacement, the initial velocity here. So u is equal to g, u sub t is equal to h when t is equal to 0. And so this is my 2D wave equation, okay, for some domain D. In this particular instance, let's just pick D to be the unit circle, right? Or sorry, rather the open unit disk, its boundaries unit circle. Okay. So physically, how can I think of this? So recall for the 1D wave equation, right? It was easy to think about this as the homogeneous Dirichlet condition would be like fixed ends, fixed string, right? And then the string vibrates. Okay, it has fixed ends. Then what is this, right? This is like a 2D membrane is stretched over some boundary where it is fixed, right? So again, u is displacement. Okay, so u of x, y, t is like my displacement. So this is saying that it is fixed along this boundary, and I can think of this region D being like a membrane, right, stretched and fixed on that boundary, and then the membrane is vibrating, right? So this is typically thought of as vibrating drum, right? So in this case, a vibrating drum that's circular, right? So this is like a vibrating drum. Okay, which is, a vibrating membrane, right? If you think of the drum being the membrane stretched over the top of the drum, right? It has fixed boundary, as in this case, and then with some initial displacement and velocity, there's a disturbance, right? Smacking of the drum or some kind of disturbance that leads to vibrations of that membrane, and those vibrations are modeled by this wave equation. So this is exactly the two-dimensional analog of the vibrating string, right, for the 1D wave equation. Okay, and so just thinking about that situation, right, a string with fixed ends versus like a membrane, right, forming a drum, vibrating, you can kind of reason with yourself. One, why that's a natural generalization, but two, also why that is a substantially more complicated thing that's going on, right? And we're going to see that directly here. So again, I have a region, of course, that I've specifically picked to be this circular disk. And so to analyze this, it makes sense to use polar coordinates, right? So this makes sense to use polar coordinates here. So in polar coordinates, r theta, what does the Laplacian become? So again, you can check this with the chain rule. It's always good practice to verify that this is actually what the Laplacian is in terms of these coordinates. But so using the chain rule, what is the Laplacian of u? This is u sub r plus 1 over r u sub r plus 1 over r squared u sub theta theta. Okay. So that's the Laplacian of u here. Okay. And so just as we did previously in prior examples, we can reformulate this problem now in terms of polar coordinates where the g and h, right, are recast depending on polar coordinates here. All right, and so the idea, as before, separation of variables, tells me to seek a solution in separated form. So if now my solution where my spatial variables are in rectangular coordinates is u, x, y, t, my solution when I've used polar coordinates for my spatial coordinates here is u of r theta t, right? So seek a solution u of r theta t where I've separated these variables, right, completely. So we'll have r of r, theta of theta, and t of t. Okay. All right, this is a pretty standard trick here. If I put this into, by now anyway, right? We've done this, I think, enough times. So if we put this into our PDE here, then what is the resulting expression after some algebra? Well, so putting this in the PDE, what do I get? I get, as usual, I get t double prime t over, I'm going to put the constant on the t term as usual. So t double prime of t over c squared times t of t is equal to, I'm going to leave the r and theta on one side here. So this is r double prime over r plus r prime over r times big R plus theta double prime over r squared theta. Okay, now, what is the PDE? Well, recall that the PDE here, if the Laplacian of u in polar coordinates is this, then the PDE itself is u sub tt is equal to c squared times u sub r plus 1 over r, u sub r plus 1 over r squared, u sub theta theta. And so dividing through by c squared here, you see exactly where this expression comes up, right? So I've divided through by c squared. I get this separated solution everywhere. I have extraneous like r, theta, and t terms everywhere they're not involved. So if I divide through by those, this is exactly what I get. Okay. So plug this into that PDE, do a little bit of algebra, and this is exactly what I get, right? As usual, this is the typical thing that happens. So just like we did last time, I look at this and I say, oh, well, here's a function of nothing but t. Here on the right-hand side is nothing but the spatial variable. So in this case, they're polar coordinates, r and theta. Both of these have to be equal to some constant. And in this case, I'm going to call this constant, instead of calling it minus lambda, I'm going to call it minus lambda squared. Okay, this will just make things a little bit nicer with our notation later. Okay, and so you might say, well, wait, like, why are you doing this, right? Because wouldn't this imply necessarily that this thing is always negative here? And the answer is yes. And so that is exactly why we're doing this, because it's going to turn out to be that this is always negative, this constant's always negative, and this notation is going to save us in a little bit. So that's why we're doing this. So if you're wondering, like, how do I know this is always going to be negative, that comes later. You could have just assumed, you could have proceeded exactly as we did before, assumed that this is equal to minus lambda for some constant lambda, and you would have ultimately found out that that thing always has to be negative, and you would appreciate this this difference in notation here as far as the formulas. Okay, I have to move my cat. He's getting a little too curious. Okay. And so, now what? Well, as we did before, that gives us one eigenvalue problem for t. But now we have these two that we haven't separated. So let's move those over. Okay, and so what this implies, let's look at this part of it. So this implies we have r double prime over r plus r prime over r times big R plus theta double prime over r squared theta. That has to be equal to minus lambda squared, and that's our constant. Well, I can move this over if you like. I can move this over in a way, so r double prime of r over r of r plus r prime over r times r plus theta double prime, or here, let's actually just go ahead and move this over, r squared theta minus lambda squared. For the same reason as before, this looks like not equal. That's not true. So these two things are equal. This is a minus sign here. So on the left, I have nothing but r here. On the right, I have nothing but theta, and this is a constant. This also has to be a constant, because again, here's theta, here's r, they're equal for all r and theta if we want a solution to this PDE everywhere in that domain. So for all r and theta defined in that domain, these two things have to be equal, which means these have to be equal to some other constant, right? And so what is the other constant? These have to be equal to some constant we'll call minus gamma. Okay. Let's see. If we're going to call this minus gamma, then I guess the way that we should do this, instead of putting the minus sign here, we should put the minus sign here. Okay, just knowing that we can do that is the more important thing. Don't get too caught up in this. We're doing this so that the eigenvalue problem for theta is the one that we're used to. That's why we're doing it this way. So if you're wondering, what am I doing with the minus signs to make this work? I just want, I want the eigenvalue problem for theta to be the one that I'm used to. Okay, actually, let's adjust this. Let's adjust this now. I'm gonna let's rewrite this slightly. Let's rewrite this in the following way. So forget about this line of confusion. Let's go back to here, and let's move the lambda actually over here and the theta on the other side, but I want the minuses all in the r's. So let's move this as the following. So this would be minus r double prime over r plus r prime over little r plus oh, I did this again. I added pluses here, but I actually wanted all of these to be minuses. Oh, yeah. So here, so that this can be equal to theta double prime over r theta. Now, just a quick notational thing, of course, these primes are with respect to theta, and these primes are with respect to r. Okay, seeing how this goes. Oh, sorry, this is an r squared. So now if I multiply by r squared here, right, then what do I get? I have, so here if I multiply by r squared, then this is like minus r squared r double prime over r minus r prime over r minus r squared lambda squared, and that is equal to theta double prime over theta. Now, on the left-hand side is something that depends only on r, right? Before, in case you were wondering what was going on here, where there was still an r over here, right? Multiplying both sides by r squared. Now, the left-hand side is nothing but a term that depends on r. The right-hand side depends only on theta. So these must be equal to some constant that I'll call minus gamma. Okay. It pays to actually do this algebra sometimes and not leave it. Okay. So all these things taken together, I get an eigenvalue problem from t from this expression, and I get eigenvalue problems for r and theta from this expression. Okay, so these two things yield 3 eigenvalue problems. So this yields 3 eigenvalue problems. What are they? Well, okay, let's go back here. So if t double prime over c squared t is equal to minus lambda squared, then I multiply through by c squared t and get t double prime is equal to minus lambda squared c squared t. And then I add that over to get t double prime plus c squared lambda squared t is equal to 0. So the first one is t double prime plus c squared lambda squared t is equal to 0. That's the first eigenvalue problem I get. Okay. What's the next one? Well, the next one comes from this, and it's the one that I'm most used to, right? So theta double prime over theta equals minus gamma. Multiplying by theta is theta double prime equals minus gamma theta. Adding to both sides, I get theta double prime plus gamma theta is equal to 0. Hey, there's my favorite eigenvalue problem, right? This is the one that I'm most used to. And then what about this last one? So for this last one, I'm going to have, let's see, how am I going to do this? Let's multiply through by r, add this to the other side, combine, divide through by r squared, and what do I get here? So directly from this, right? So minus r squared, let's immediately go multiplying through by r, dividing by r squared. This would be minus r double prime, right? Minus 1 over r, r prime, minus lambda squared r is equal to minus 1 over r squared gamma r. So that is the thing that I get. If I add this to the other side, factor out this r term and these last term combined terms, what is the equation I get? I get r double prime plus 1 over r prime plus lambda squared minus gamma over r squared times r is equal to 0. So unfortunately, that eigenvalue problem is a decent bit more complicated than the others. Okay. Well, because this is more complicated, the idea is that I want to solve this one first, right? This is the one that I'm most comfortable with. Okay. Well, here's the question. What kind of boundary conditions are we going to look for here? So what are my boundary conditions here, right? That's very important for these eigenvalue problems. It was always a question of BCs. Well, last time we did a separation of variables problem where we used polar coordinates. We saw that switching to polar coordinates actually yielded some implicit boundary conditions. Now, if we go back to our original problem, you might say, wait, the boundary conditions are this one, which is saying that u is 0 on this boundary circle. So how does that translate to these boundary conditions for these eigenvalue problems? Well, we're going to see how that works here. So first, for this, I get implicit periodic boundary conditions because theta is a periodic thing, right? Just that's how polar coordinates are defined. And so I get implicit periodic BCs. So this is theta of 0 is equal to theta of 2 pi, and theta prime of 0 is equal to theta prime of 2 pi. So I'm not told exactly what they are here, I'm just told that they're periodic. What about here? What do I get? So let's see here. Well, let's go back. What is r describing? R is in terms of the radius of this thing. And when the radius is equal to 1, how do I rewrite the boundary of my region in terms of polar coordinates? This is really the set of r thetas such that r is equal to 1. Right? That's exactly what this set is. And so when little r is equal to 1, u needs to be 0, right? And so I get the boundary condition that is r of 1 is equal to 0. Okay. But then what about like r of 0? Right? So r of 1 is what I get. Now, the problem here is the entire boundary is encapsulated by this boundary condition here. So this BC, right, is basically entirely encapsulated here. It turns out that we're going to need something else. So this is not going to be enough. We are going to also need that r of 0 is finite. Now, the reason we need this won't become clear until we've talked about this equation a little bit more. Okay, but you're basically going to see that this picks out the solutions here that we want. Because it turns out that this thing has some solutions that are special. They come as two linearly independent solutions, but only one of those two families is actually bounded at the origin. And so this is what we need in order to pick out the one we want from here. Okay, but technically this is the boundary condition we get. Okay, so firstly, what do I do? Right, and I have no BCs for the temporal one, which is typical of these problems. So, right, because, I mean, there's no boundary in time. And so, what do I do? I pick the one that I know how to solve, right? So, so I do this one first. So solve the theta equation first. If I do that, what do I get? I get eigenvalues as before. Gamma is n squared, where n is 0, 1, 2, 3, and so on. All right, so 0 is an eigenvalue here. And eigenfunctions corresponding to these, which are theta sub n of theta, which is given by constants c times cosine of n theta plus d sine of n theta. Okay. Now, this is my completely general case here for these periodic conditions. Of course, this is what we get in the periodic case for these eigenvalue problems is the full Fourier series coming out. Right, and this is for to make this work. Let's say that these are eigenfunctions for n equals 1, 2, 3, and so on. And notice that when n is equal to 0 or when gamma is equal to 0, right? So what does that mean? This theta naught is constant. Okay. Okay, so this thing is constant for the 0 eigenvalue, and for all the others it looks like this. Okay. So now, so that takes care of my theta equation. So then what about my eigenvalue problem, right? So this one came from my list because this was a type of eigenvalue problem I knew how to solve. What about this one, though? right? So what about the R equation? So let's rewrite it first of all. So maybe I'll say here. So now let's solve the eigenvalue problem for R. Okay. And so rewriting this, the eigenvalue problem looks like R double prime plus 1 over R prime plus lambda squared minus, so going back, we have found that gamma is n squared. So now that we have found those eigenvalues, we can turn our attention to the eigenvalue problem for R by plugging those eigenvalues in here for gamma. So this would be lambda squared minus n squared over R squared. This is lambda squared minus n squared over R squared times R is equal to 0 with boundary condition R of 1 equals 0, and I'm going to impose this extra condition that R of 0 is finite. Okay, so note first, if lambda equals 0, the only solution to this equation is actually trivial. I.e. it's identically 0. Okay, with this boundary condition. So the only solution to this equation plus R of 1 is equal to 0 is trivial. Okay. And so we only need to worry about when lambda is positive. So we only need to consider lambda greater than 0, right? So we don't have to worry about the 0 eigenvalue here. Okay, and since we know that this lambda is greater than 0, going back to our 3 eigenvalue problems, it means that when we turn our attention to the t problem, we only have to consider that case. We don't have to consider the 0 eigenvalue case here. Okay. And so now I have to find these lambdas from the R equation. So let's do this, right? So let's first, we change variables. By defining rho to be lambda times R. If we do that and rewrite this equation in terms of this new variable rho, this equation becomes the following. It is R sub rho plus 1 over rho R sub rho plus 1 minus n squared over rho squared. All of this is to get rid of the lambda squared here. R is equal to 0 for n equals 0, 1, 2, 3, and so on. All right, that was true up here too. That is the eigenvalue problem we get. This eigenvalue problem is an equation that is very special. This is called Bessel's equation. Is the name of this eigenvalue problem. Okay. It turns out that here are some facts. For any n, this equation has two linearly independent solutions. Second fact, only one of them is bounded near r equals 0 or rho equals 0. Only one of these for each n is bounded near rho equals 0. In fact, this is actually smooth. It is smooth, which means it has infinitely many derivatives. Okay. All right. So, now what? Well, this second fact that only one of these is bounded near rho equals 0, this is where this condition that I've imposed comes in, where if I want this to be the case, then for each n I have two linearly independent solutions to this equation, but it's clear which one I want to pick. I want to pick the one that is bounded near rho equals 0, i.e. is smooth. That, for a given choice of n, this is called a Bessel function of order n. Right, so this is called the corresponding Bessel function of order n. So for each n, this smooth solution to Bessel's equation is called the Bessel function of order n, and is denoted as J sub n of rho. In fact, this was probably not done in your typical undergrad ODE course. It really depends on what the interest of your instructor was in actually exposing you to these various things. This is kind of some of the material that could have been tossed in, right? It's some instructors want to focus on Green's functions, others want to get to systems quicker, right? It really depends. But in an ODE theory class, you could do this. You could actually solve Bessel's equation. So a solution to this eigenvalue problem can be found. In fact, the solution, these Bessel functions, so it can be shown that J sub n of rho is equal to the sum from k equals 0 to infinity of minus 1 to the k times rho over 2 to the n plus 2k over k factorial times n plus k factorial. Okay. So that's kind of a slightly curious formula there. Okay, so now while this might look scary at first, it can be shown that this is indeed C infinity, i.e. smooth, having infinitely many derivatives, right? As nice of a function as you can imagine. Now, these are going to be my eigenfunctions, right? These are going to determine my eigenfunctions. These are going to determine my eigenfunctions. R sub n of r. And so we have eigenfunctions arising in this way that are given by these Bessel functions. Well, there might be some alarm here raised, right? Because you say to yourself, well, hey, up until now, right, the eigenfunctions that we have used have all been like sine and cosine mostly, right? And sine and cosine or exponentials or, and you talk about exponentials, you're talking about hyperbolic sine and cosine too. But really sine and cosine is kind of, these were our eigenfunctions. So when you talk about eigenfunctions, in order to be able to actually carry out solutions to these problems, to find solutions to these problems, you needed the fact that these eigenfunctions had these orthogonality relationships, which meant that you could actually find the coefficients needed, and also you needed some, you needed the orthogonality relationships, and you needed the fact that these eigenfunctions spanned the space of reasonable functions, right? So going back to our original statement of this problem, if g and h are going to be, like generic functions here that I'm picking, the idea is that somehow a solution is going to involve the g's and h's, and in this analysis, right, that is going to involve like being able to find coefficients that make imposing this initial condition make sense, hold for that solution formula that we get. And that's going to involve finding the right coefficients, which is going to mean viewing basically an expansion of these functions in terms of those eigenfunctions, right? Well, sine and cosine, right, span the space of reasonable functions. The question is whether functions like this do, right? And we'll see that they do indeed, but maybe just inherently looking at this, you're nervous and don't like it just because of what it looks like. It's defined as this like infinite series, right? This like power series type thing in terms of rho. So you look at something like that and you just naturally kind of dislike it, right? You naturally kind of dislike it because, well, it's just given to you in a form that, this is not like sine and cosine, right? Well, of course, I could say, what if I gave you an eigenfunction that looked like this instead? All right, so what if I gave you an e sub n of x and said my eigenfunction is like the sum from, say, like, k, we'll say like k equals 0 to infinity of like minus 1 to the k times like, I don't know, we'll say like square root of lambda sub n times x to the 2k plus 1 all over 2k plus 1 factorial. What if I gave you an eigenfunction that looked like that? What if I gave you an eigenfunction that looked like this? So that f sub n of x is like the sum from k equals 0 to infinity of, so this is like, yeah, the sum of k equals 0 to infinity of like, well, this is, let's make this minus 1 to the k times square root of lambda sub n x to the 2k over 2k factorial. Okay. What if I gave you eigenfunctions that look like this instead of this, right? Would you be happier with these? Would you say that these are like totally different kind of objects than this? Right? Well, I mean, maybe you'd be equally unhappy. But if you thought about this for a second, you'd realize, wait, maybe I'm not that unhappy. Because what are these? Well, what is this? This is sine of square root of lambda in x, and this is cosine of square root of lambda in x. Oh, right. I mean, what is sine and cosine after all, right? So yeah, you could think to yourself, when you think of sine and cosine, I'm sure the first thing that probably pops into your head is unit circle and blah, blah, blah. You've defined it in terms of angles on unit circle and all this. But if, you know, if we're talking analytically, right, that's defining sine and cosine like that, it's kind of annoying. Like, it's great geometrically to think of the trig functions in that way because that's kind of how they're introduced to you, you know, the first time you see them. But and like analytically, right, when we want to actually compute with them, one could just take these power series expansions. In fact, many textbooks do this. You could just take these power series expansions as the definition of sine and cosine, right? Like, that's the definition of sine and cosine. That's exactly what they are. They are those power series, right? You can prove all of those facts about sine and cosine that you know and love directly from these power series expansions for sine and cosine. And so, if the very first time you'd come across these eigenfunctions, sine and cosine, I wrote them in this form, then maybe you'd be like, oh, right, that's kind of annoying. Why does this expression come up so much? Why does this expression come up so much, right? Isn't that weird? Well, it's just sine and cosine, right? That's all it is. So there's no reason to be too afraid of these power series, right? Power series that look nasty can actually be really nice, and then these Bessel functions are just just a slightly different type of power series, right? So it's just a slightly different form here. Okay, all right. And so these are going to determine my eigenfunctions. Let's see exactly how that works here. So in terms of these Bessel functions, my eigenfunctions for R now, before I even write this down, you might say, wait a second, right? You gotta tell me what the eigenvalues are before you can write out the eigenfunctions. Well, so here's where our picture gets a little complicated, because we're going to have implicit relations on these eigenvalues. So I'm going to be able to write out the eigenfunctions, and then I want to talk about how my eigenvalues and finding the eigenvalues might come about here. So in terms of these Bessel functions, my eigenfunctions are R sub n of R is J sub n of lambda R, right? Recall that rho is lambda R, right? And so the reason for doing this change of variables in the first place is so that I have this relationship between my eigenfunctions and these Bessel functions, right? So here it is, right? And that's true for n equals 0, 1, 2, so on. Okay. Now, what about our BC? Our BC for the R eigenvalue problem. Well, what was it? All right, let's go back. What was my BC for the R eigenvalue problem? So here's my 3 eigenvalue problems. For the R eigenvalue problem, my boundary condition was R of 1 equals 0. So R sub n of 1 needs to be 0 for any n, but that would mean that j sub n of lambda times 1, so j sub n of lambda is 0 for any n, i.e. lambda are roots of these Bessel functions. Okay. But what do these Bessel functions look like? Well, let me go to my bookshelf real quick. This is some ancient edition of this. So this is, I don't even know what edition of Strauss's PDE. This was like the PDE book in a lot of ways for undergrads. On the cover of it has this graph, right? What is that? It's a Bessel function. So they look like this. Okay, what else? It's another maybe picture to show you what it is that's going on here. So in your textbook, let's see, the version of the hard copy textbook I have has slightly different page numberings than the e-copy. So let me show you where it is. So here we go. This is what the picture looks like. So this would be the picture for the Bessel function j sub 1. These would be roots. I'll discuss the subscripts here in a second. And then j sub 2 has roots like this, given by those lambdas. Okay. So the first positive one is what we take as lambda 1, 1 here. We call this lambda 2, 1 because it is the, notice the subscripts are all 2, 1, 2, 2, 2, 3, 2, 4, 2, 5. Here the subscripts were 1, 1, 1, 2, 1, 3, 1, 4, and 1, 5. So the 1, 1 or 2, 1 are taken as the smallest positive eigenvalues associated to these things. And then the ones subsequently count up like this. But there's infinitely many. This continues on, just like that textbook cover I showed you. This continues on. And so there are infinitely many of these things. And so j sub n of rho has an infinite number of positive roots for each n. We will label these as follows. So we will label these as, there's a smallest one for some Bessel function of order n. The first one is lambda sub n 1. The next one is lambda sub n 2. The next one is lambda sub n 3, and so on. By the very nature of these, all of these have to be strictly distinct right? They can't be the same because of how these Bessel functions look, and these are roots, and none of these agree, right? I.e., what we mean is that counting, starting from the smallest positive one and going to the right, lambda sub nm is equal to the mth root of the Bessel function of order n. J sub n of rho. Okay. And so, for n equals 0, 1, 2, and so on, for m equals 1, 2, and so on, we have eigenfunctions with double indices. R sub nm of R is equal to J sub n of lambda sub nm times R. So there's my eigenfunctions. Now, assuming that we have found those eigenvalues in this way as these roots of Bessel functions, right? Then we plug those eigenvalues into, right? So I use my lambda sub nm eigenvalues here in this t eigenvalue problem, and I get eigenfunctions for t as well. So lastly, going back to the t, so going back to the t eigenvalue problem, I get t eigenfunctions that look like what? So let's consider for a second, what type of eigenfunctions did I get for an eigenproblem like this? These were sines and cosines, right? Because this is, remember, this isn't the heat equation, so this is now second order instead of first order. If this is first order, I get exponentials out of this, right? For second order, I get sines and cosines. And so this is a cosine of lambda nmt. Notice that because I've defined this as lambda squared way back then, I don't get a square root here. I just get lambda, so this is nicer. Plus b sine of lambda nmt. Now again, you might complain because this is kind of sort of annoying because we haven't explicitly found the lambdas, right? They're defined in this implicit relation way as roots of these Bessel functions, so we don't have like a nice closed form expression for these eigenvalues. But nevertheless, let's continue on like this, right? So then what are my separated solutions now, right? So thus, for each n equals 0, 1, 2, and so on, and m equals 1, 2, 3, and so on, I have separated solutions u sub nm of r theta t that look like what? Well, these are going to look like, I'm going to write the t first just because, so this would be t nmt times, we'll write r nmr times theta in theta, right? And so what do these look like? So let's just refresh my memory, right? The theta n's eigenfunctions look like this. The r eigenfunctions involve these Bessel functions. And the t eigenfunctions look like this. And so this is like really, really kind of nasty, but it's a cosine of lambda nmt plus, and these coefficients are going to be, these coefficients are going to be indexed by n and m as well. So a sub nm cosine of lambda nmt plus b sub nm sine of lambda nmt. Okay. I have messed up here. This is not lambda nmt. This is lambda nm. I forgot the c in my eigenvalue problem, right? There's a c squared term here. So there's a c here. That's pretty easy to add in. So there's ct's here. Times r sub nm r. This is given in terms of the Bessel functions. Right? So this is j sub n of lambda nm r. Okay, and then now I have my theta eigenfunctions, which again, this is what they look like. These constants c and d also going to be indexed by n and m. So this is going to be c sub nm cosine of n theta plus d sub nm sine of n theta. That is what my separated solutions look like, where these a, b, c's, and d's are these constants. Okay. And so, if I put this all together, what do I get? Right? So, if I want to write u of r theta t, this is going to be the sum from n equals 0 to infinity, the sum from m equals 1 to infinity of u sub n m r theta t. So I'm summing these over n and m. So then what do I get here? This is, well, for the n equals 0 term, I can pick that out and consider that separately, and then do the double sum for the n equals 1, m equals 1 term. So for the n equals 0 term, I'm going to get the 0th Bessel function showing up. So this is going to be what I'm going to get. So like I said, pick out the n equals 0 term on its own. What I'm going to get is the sum from m equals 1 to infinity. U of 0 m is going to be, so if I have used 0 here for n, this would be cosine of 0, so that's 1. This would be sine of 0, so that's 0, so the d's go away. So this would be c sub 0 n times sine, and then a sub 0 n times cosine here, where that I've basically absorbed this a and b here in this expression. So what do I get? I get j of 0 lambda 0 m r times a 0 m cosine of lambda 0 m ct plus c of 0 m times, well, let me see here. So, if you like, how I could, here, I can write this like this. B of 0 n sine lambda 0 mct times c of 0m, right, plus the double sum from 1 to infinity from both of these of everything that's left, right? So the Bessel functions times this double product here, right? So you could view it as like, we'll view it as a sub, I'm going to write it like this, c sub nm cosine of n theta plus d sub nm sine of n theta distributed on the first term. So that's times a sub n m cosine of lambda 0 mct plus c sub nm cosine n theta plus d sub nm sine n theta times b sub nm sine of lambda, sorry, not 0, and this is nm ct. Okay. And so now let's introduce the initial conditions finally and see what this means. So going all the way back to our initial conditions here. All right, so this should be my solution to this equation. And our initial conditions were given by generic functions g and h. So initial displacement, initial velocity when t is equal to 0. And so imposing that t equals 0 condition on this massive expression, what do I get here? Well, it's actually easier maybe to impose it here, right? So let's impose it here on this product rather than seeing what it looks like in this sum. So on this separated product, if t is equal to 0, I get t of 0, which is a constant, times my Bessel function here as normal, times this sine of 0, 0 times cosine, right? Here. So if t is equal to 0, this is left unaffected. So this is going to be times cosine. When if I take the derivative of this with respect to time and impose that same condition, it's going to be the exact same thing times sine, right? And so imposing the initial conditions on my separated solution, what do I get? I get that u sub nm of r theta is, or maybe here I should say that u sub n of u sub nm r theta 0, right, is going to be the Bessel function times cosine of n theta. and I'm going to get a product here between this and v sub n m, we'll call it r theta, which is Bessel function sine of n theta. These are eigenfunctions for minus the Laplacian on D with Dirichlet boundary conditions. Okay. Turns out these are orthogonal in some sense. They span reasonable functions. Okay. Thus, we can find coefficients a and m, b and m, c and m, d and m, satisfying the initial conditions. And so that is the solution. This massive gargantuan thing in terms of these Bessel functions, right, gives me the solution to this 2D wave equation. Now, the first thing that I want to note here is, like, what is it that's going on? So remember, so here's the big question. Right, what is it that's going on? Because it is extremely easy to get lost in all of the notation and all of the analysis and to lose sight of what it is that's actually happening. So what is it that is going on here? Remember, for the string, we talked about normal modes, natural frequencies, right? So recall, for the vibrating string, with fixed ends, we discussed normal modes and natural frequencies. And that we could determine these things, we could talk about these things in terms of the eigenvalues. But the eigenvalues that we found in that case were very simple, right? They were straightforward. In the 1D case, we had them explicitly. There was not this implicit relationship and blah, 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 right? Okay, well, we can do the same thing. So we can do the same for the vibrating drum with fixed boundary. But the situation is just way more complicated. Right? So what's going on is just way more complicated. Which is why we get these expressions that we get. Okay. Well, it turns out that actually these things I wrote on the previous page, these spatial eigenfunctions, okay, these spatial eigenfunctions we get for this problem, these are my, so these actually are my normal modes, right? The spatial eigenvalues, or sorry, the spatial eigenfunctions u sub nm and v sub nm are the normal modes. Okay, and the natural frequencies are lambda sub nm times c. Those eigenvalues we found as roots of Bessel functions. Okay. What is the interpretation of these things? The normal modes can be thought of as like natural shapes for the drum, whose specific character is determined by its size. Here we're just using this is just the unit disc model, unit disc membrane, right? Drum membrane, and C, which is this this constant that depends on the material used, its density, tension, things like that. Then suppose that we start with some initial data, right? Then the point is that at any later time, the solution would simply be a constant times the initial shape if the initial data we chose was one of these normal modes, right? So suppose we began with initial data that is g of r theta, which is one of these Bessel function defined spatial eigenfunctions. So we'll say cosine of n theta here. Okay, and we'll say that h, its velocity, is identically equal to 0. So velocity is 0. The initial shape is this. Then at any later time, the solution would be, what are we going to do here? We're about to make a statement. We were able to make the analogous statement for the 1D wave equation. What are we about to do? We are going to use the fact that these things satisfy orthogonality, right? They are an orthogonal basis for my space of functions, to look at this thing and say, well, if the g that I pick is one of these things, then it's going to get plugged into this formula somehow for these coefficients, and everything is going to be 0 except the thing that it agrees with, the thing that it matches, right, because of orthogonality. And so what I end up getting in this expression is that this thing is orthogonal to everything except the thing that it matches, which is going to be, that's going to come about where? That's going to come about on the, this is going to be like the sine of lambda nmct term here, right? It's going to be orthogonal to everything. It's going to, but it's going to be cosine of n theta times sine of lambda nmct, right? So what I get is u of r theta t is j sub n lambda nm r cosine of n theta sine of lambda nm ct, which tells me what? That this is going to be a constant times the initial shape, right? So it's going to be, so here for a fixed t, this is some constant sine lambda in mct, right, if t is fixed. This is constant times my initial shape. So just like last time, I have my initial shape is preserved in the sense that the initial shape is or the solution at any time, the displacement at any time is given by just at a fixed time a constant multiple of my initial shape. Okay. The zeros of these normal modes are called nodal lines. Okay, the zeros of these normal modes, these eigenfunctions, are called nodal lines. And they represent points on the drum that stay fixed. So they represent points on the drum that remain fixed. Okay. So for a vibrating string, these nodal points, we didn't really talk about them that much because they were always a fixed distance apart, right? And that's because the eigenfunctions in questions were sine and cosine, and sines and cosines have a fixed distance between any of their zeros. The nodal lines are not at fixed distances, and that's because of how the Bessel functions work, right? The spacing of the zeros of the Bessel functions, unlike sine and cosine, these things are not uniformly distributed. There's not always the same distance between subsequent zeros. Okay? And so that is a consequence of these Bessel functions being the way they are. Let me show you a picture of 3 different n equals 0 modes that illustrate nodal lines corresponding to zeros of the 0th order Bessel function. So here is what's going on. All right, so in each case we're looking at the 0th order Bessel function. Okay, here's the 0,1 mode, the 0,2 mode, and 0,3 mode shown separately. What these things look like. See, these circles here correspond to, these are the nodal lines. Okay, and so you can see exactly how they correspond to zeros of this. So here is 0 for the 0,1 mode, so that's, here's the fixed, right? So this is like the fixed boundary, if you like. Here I have another ring of fixed points here, and so in the vibrating drum, this is what the picture would look like. Here, because I have zeros for the Bessel function here and here, this corresponds to these nodal lines that look like concentric circles here. Right, but again, the spacing is not going to be the same for these, right? If I continue this process on, these zeros are not equidistant. So these concentric rings, even though it might look like it in the picture that they're equidistant, they're not going to be, right? If I expand this, like some of the rings are going to be closer to other rings. Okay, and so that is how these nodal lines go. Okay. Now, one last thing to say, he even says this directly in the textbook, which is to say, don't be afraid of Bessel functions. Hopefully the bit that I said about relating them to sine and cosine, right, about how if you thought about sine and cosine in terms of power series, if the power series nature of Bessel function kind of shocked you, right, or you didn't like that for whatever reason, well, remember that sine and cosine you're just used to, right? You know their properties. But you can get used to Bessel functions in the same way, right? And just like sines and cosines are just special names for those power series, if you want to view it like that, right? Sines and cosines are just the special name for those particular power series that we've given because we recognize that they came up a lot. They're very useful. Similarly, calling it a Bessel function of order n is just the name given to that particular power series. And so that is one way of thinking about it with experience, right? You will deal with Bessel functions and be aware of all their various properties in a way analogous to sine and cosine. And so, you know, nothing to worry about here, right? In fact, if you're using MATLAB, if you're using Python, basically whatever you're doing, these things are implemented. When it comes to computing, Bessel functions are all over the place. And almost anything you do in any kind of software package is going to include, you can actually, almost all these will have commands to call on any particular Bessel function that you want. The eigenvalues, lambda sub nm, of course, you're not going to write out a closed form expression of them, but hey, guess what? You can get these to any accuracy you want, right? You can have these, you can compute to whatever accuracy you desire using a computer. So even though you don't have closed form expression of them like we did for the simpler cases, who cares? We're able to figure them out, right? We're able to compute with them, so it's fine. And so that is the kind of our, what did we do in today's lecture? We solved a single equation, right? 2D wave equation, but out of that came kind of our first real example of eigenfunctions that were different than sine and cosine. The reason why it's useful to see this is because this overarching method that I've mentioned, expanding functions in terms of eigenfunctions coming from a symmetric differential operator on a Hilbert space, compact symmetric operator on Hilbert space, that is a technique, or that is a thing that is ubiquitous in math, science, a lot of fields. So this is something that is very, very important. In fact, we'll start tomorrow's lecture with a discussion of this problem, whether or not you can hear the shape of a drum, right? So maybe that's the lead-in to tomorrow's lecture, which is a question: can you hear the shape of a drum? That is stated kind of informally. If I had, say, a perfect way to detect the frequencies, the overtones, and the actual quality of the, say, beats made with, right, if I could understand perfectly all of those qualities from hearing the drum, could I actually tell the shape of the drum if I didn't know it? Could I tell what the shape of the drum looked like? Right? So that is the question to consider. Right? And so given the fact that we were talking about vibrating drum today, maybe you should think that it's related somehow. This is a direct result of these eigenvalue problem analysis we've been doing, and it turns out, of course, in this case, these frequencies we're talking about can be given in terms of the eigenvalues. So really, this question, can I hear the shape of a drum, can be reformulated as a statement about eigenvalues. Right? So this is really a question about eigenvalues. This is really a question about eigenvalues and eigenfunctions. Okay, and we'll see that tomorrow. All right, so that's it. I'll see you all tomorrow.